Good morning friends, I welcome you all for another lecture on the course Microprocessors and Microcontrollers. In this class I am going to discuss about the instruction set of PIC microcontrollers. We know that PIC microcontrollers are a RISC type of controllers. One of the important features of a RISC systems or a RISC controllers or RISC processors is the number of instructions present in their instruction set was less. So that your PIC microcontroller comes under RISC type of controllers, so that the number of instructions present in the instruction set are less. Those are total 35 instructions. So that is my first point is PIC microcontroller instruction set contains total 35 instructions. These 35 instructions I am going to divide it into 3 groups for easy learning of the instructions which are present in this instruction set. Those instructions are byte-oriented instructions, bit-oriented instructions, constant or literal and control instructions. For our simplicity, again I am going to divide this one into 2 types of instructions. That is, if I write 3.8 or 3, that is a constant or literal instructions, and number 2 is number 2 or 3.B or 4, it is control instructions. Control instructions. So I divide the last group into like this. If you consider these 2 are separate, then the total number of groups here are 4. That is byte-oriented instructions, bit-oriented instructions, constant or literal instructions, and last one is control instructions. Before discussing these instructions one by one, I would like to discuss about some points regarding to these instructions. In that, my first one is each and every instruction size is 14-bit. Each and every instruction size is 14-bit. That 14-bit instruction is divided into 2 different fields. One is opcode field. This opcode field, what it specifies is the type of operation. The opcode specifies the type of operation. And the second type of fields are operand fields. Those are one or more operands which specify sources and destinations of data. That means every instruction you may identify operation code field as well as operand fields. The same thing here also exists. Each and every instruction size in this PIC instruction set was a 14-bit. That 14-bit instructions may divide it into 3 groups. And each and every instruction may contains 2 different types of informations. One is a opcode, which indicates which specifies the type of operation, and second one is operands. Those are one or more operands present in the instruction. Those are specifies sources and destinations of data. And one more important thing is in this PIC instruction set, we are using different letters or different characters in a small letters or lowercase. In that, one of them is F. Especially this we identified in both the byte-oriented as well as bit-oriented instructions. What this indicates that we are going to identify. So byte-oriented instructions, F designator represents a file register. F represents a file register, that is nothing but a RAM or a particular location in a RAM. So F designator represents file register, and D designator, this is another one. D designator represents that is a destination. That means in case of PIC, we won't say the operand which follows operation code is a destination, or the operand which exists in the last, that is a destination. We won't say like that. We can go and use any operand of an instruction, maybe destination, that is purely depends on a D designator. This D designator decides which one is your destination. Your destination is the first or your first destination is second. It is not like that exactly. Your destination is either working register or it's maybe file register. That is a purely depends on a D. So what is a D? This D is equivalent to 0. That means you written D is equal to 0. No doubt the destination of that particular instruction is working register W. I repeat, D is equal to 0. Always the result of that instruction execution goes to working register W. Otherwise, that means if D is equal to 1, the result always goes to file register F. So that is important one is D. And next in bit-oriented instructions, bit-oriented operations, along with F, we are using one more character which is B. What this B indicates? B represents a bit field. Because these are bit-oriented instructions or bit-oriented operations, these are doing operations straight away on specific bits. That means we are not only doing operations on all the bits which are present in the file register, we are specifically doing an operation on a specified bit. So in that case, that B represents a bit field designator which is select the number of the bit affected by the operation, while F represents the address of file. That means if I consider a file register which size is equal to 8 bit, out of that 8 bit, this bit field represents only one of specific bit out of that 8. That address is indicated by bit field, and that F indicates the file register itself. And next, for constant or literal and control related instructions or operations, we are using one more character that was called K. This K represents a literal or a constant whose size is either 8 bit or it's maybe 11 bit. Again, I come across last groups, that is constant related instructions or control related instructions. Here we are identifying one more character that is called K, that is called a literal or a constant whose size is equal to either 8 bit or it is equivalent to 11 bit. So next, I would like to discuss about the formats of these 4 different varieties of instructions. How the format looks like. That means we know that an instruction size is a 14 bit. How those 14 bits are organized. So that I was going to discuss for these 4 different types of instructions, one after another. First, my discussion starts with byte-oriented file register operations. That means if I was doing operation on bytes, that is one thing, and the instructions, the operand is a file register along with working register W. If that was a scenario, how the bits of that instruction was formulated, how the bits are divided between different fields in such a type of operations based instructions. So see here friends, the total instruction size is a 14 bit, that indicates bit D0 to D13. It can be divided into 3 fields. In that my least significant 7 bits, that is D0 to D6, called F, that is called a file register. File register is nothing but a register that was present in a register bank. We know that each and every register bank size is equal to 128 bytes. To identify a particular register or to identify a particular location in that particular register bank, no doubt I need a 7-bit address, because 2 power 7 is equal to 128. So that's why here the least significant 7 bits are dedicating for file register F. So that here we are written as file F is equal to 7-bit file register address. That means a register bank size is 128 bit. So 128 bytes. To identify each and every byte of that register banks, I need a 7-bit address. That's why least significant 7 bits are dedicating for file register address. And next bit, that is dedicating for D. D indicates a destination. We know that D is equal to 0, your destination is working register W. Or if D is equal to 1, your destination is nothing but F itself, that is a file register itself. With this, we are covering total 8 bits out of 14. We left with another 6 more bits. those 6 more bits from D8 to D13. So these are 6 bits are dedicated to operation code. That means the number of possible combinations we are getting here is 2 power 6, which is equal to 64. But the number of instructions present in your instruction set was 35. In order to address these 35 instructions, we must have a 35 operation codes. To identify that 35 operation codes, again I need a 6-bit formation. So that's why here the number of bits we are dedicating for representation of operation code was 6 bits. So I hope you understand how these 14 bits are divided. So least significant 7 bits for file address, and next bit for destination address, and the next one is 6 bits for representation of operation code. Yes. Next, I would like to discuss about bit-oriented. Bit-oriented file register operations. That means we are doing operation on bits of file registers. So then how our instruction format looks like. See here guys, again it is also divided into 3 fields. The least significant are 7 bits, again dedicated for file register. This file register is nothing but a register which was present in a register bank. We know that bank size is 128 bytes. To address a register in the bank, no doubt I need a 7-bit address like our previous case. And next up, D7 to D9, that means 3 bits. These 3 bits are used for bit field. Why? Because if you consider an 8-bit register, the number of bits present in it is already, I told you, 8 bits. To address each and every bit, I need a 3-bit address. So that what that 3-bit address is, that indicates this. 7 bits and 3 bits are odd, then the number of bits here finishes is 7 plus 3, that is equivalent to 10. We left with another 4 more bits, that is a D10 to D13. These are dedicated to operation code. These are dedicated for operation. So that is about this particular format. Next I can go for third one, literal and control operations. Especially here I would like to represent this is a format for literal based operations or constant based operations. Literal based operations or constant based operations. Those are our 3.8 instructions. The format is like this. Here just I have only 2 fields. One field is for representation of literal or a constant K field of size 8 bits, that is a D0 to D7. We left with another 6 more bits, that is D8 to D13. These are comes under operation code field. So here important thing is here friends, these type of instructions also do the operations on bytes. Because of that here your constant or a literal size is equal to 8 bits. Once you remember friends addressing modes concept, in immediate addressing mode related instructions, the data was directly placed in the instruction itself. In those addressing mode based instructions, your data size is an 8-bit, so that here your literal or constant size is 8-bit. So that is an 8-bit. Here is already from that same structure of architecture. When I am talking about addressing mode, this once one of the operand is immediate data, another operand is always working register W. So that working register W may act as a destination also, or it may act as a source also. So that here in that W register is incorporated in this itself, so that I need not be dedicating for representation of that W register for a bit in this format itself. So see here friends, least significant 8 bits, that is D0 to D7, are purely dedicating for representation of our constant or our immediate value or our literal value of size 8 bits, and the rest of our 6 bits are used for representation of operation code. That's why see here friends, K is nothing but 8-bit immediate value. And coming to the last variety, is especially for control related instructions. That is a branching instructions. So that's why here I can call as call and go to instructions. This call and go to instructions comes under control instructions, which are nothing but branching instructions, which are nothing but jump instructions. In this case also you may identify that Our instruction may have only two fields. Least significant 11 bits, that is a D0 to D10, are dedicating for representation of literal or a constant K. We left with another 3 more bits, that is a D11 to D13, those are dedicating for operation code. So here important thing is, these are used for branching instructions. These instructions provides a destination address in our program memory. In case of our PIC controller, whatever the program memory that was available, that program memory was organized into different pages. A page size is equal to 2 kilobytes. So in order to address a location in a 2 kilobytes of a page, I definitely need a 11-bit address. So that 11-bit address we written in the instruction operand field. So our instruction may have only two different fields. One field is for operation code and another one for operand. This operand here is 11-bit literal or 11-bit constant. So these are our instruction formats. Next we'll see what are the instructions. Comes under these 4 different varieties. So bit-oriented instructions. This is an instruction and this was a description. See here friends, add WF space F comma D. If I write an instruction like this, add WF space some reg 0 comma D0. If that my instruction was, that means do addition between working register W and a file register or not. After addition, your D value is equal to 0. Once a D is equal to 0, our result was stored in working register W. So the meaning of add WF means add working register W with file register F. The result is stored either in working register W or it is in file register, that is depends on bit D. So that's the meaning of this. And similarly my next instruction is add WF space F comma D. It is similar to previous case. In previous case I was doing addition. Now by using this I was doing logical AND between the content of working register W and the content of file register F. After logical ending, the result either stored in a working register W or it was stored in file register F. That is purely depends on D. If D is equal to 0, the result is stored in working register W. If D is equal to 1, the result is stored in file register F. That's it. And similarly, the next one is CLRF space F means clear file register F. That means, for example, if I write my instruction is like this, CLRF space REG1 means clear register 1. That means register 1 is loaded with a 00H because all the register sizes are 8 bits. So what are the file register we are mentioning in the instruction operand field, that register was cleared. That means that register was loaded with the 00H, or that register all bit positions are filled with 0. So that is the meaning of this. Next is CLRW. That means a clear working register W. That means a load 00H onto working register W. Load working register W each and every bit position with a 0. That is the meaning of this. Next CMPF space F comma D. That means it complement the file register content. Here complement in the sense one's complement. After complementation, what was the result we was getting at the output? That result either stored in the same file register F itself or it is stored in working register W based on D value. And next one is a DECF F comma D. That means decrement the file register content F by 1. After decrementation, the result is either stored in a file register F or it can be stored in working register W. Again, that is purely depends on bit D. If D is equal to 0, after decrementation of a file register F, the result was stored in working register W. Otherwise, the result stored as it is in file register F itself. And next one is DECF SZ F comma D. That means first you decrement file register F by 1 and thereafter, after decrementation, the file register value was 0, then skip the instruction which follows this. After decrementation, the file register value is not equal to 0, then as usual it will go and execute the instruction which is there after this. I write a small example for better understanding. Let you can assume, friends, this is a program. Somewhere else here I have an instruction is DECF SZ space REG 0, 1. This is my instruction is. That means first I must decrement register 1 content by 1. If it is 1, D is 1, that means what of the result after decrementation that again stored in this register R1 itself. And thereafter I will go and check this R1 value, register 1 value. If the register 1 value is equal to 0, then I skip this instruction. I will go and execute this. If that register R1 value is not equal to 0, then I have to go and execute this instruction. There is no chance for skipping of this. That's the meaning of this particular instruction is. And similarly, INCF F, D, that means increment the content of file register by 1. After again incrementation based on D value, the result either stored in the file register F or it can be stored in working register W. And next one is INCF SZ space F, D. So it is extension for previous one. Here also we increment the file register content by 1. Again based on D value, the result is stored in file register F or it can be stored in working register W. Thereafter, it will go and verify the result is equal to 0. It will skip the next instruction, otherwise it will execute the next instruction. So that is these instructions. And we have another instructions in this byte-oriented instructions. That is IO or WF F, D. IO means inclusive OR. That means logical OR. This is what is logical OR. Logical OR between the content of working register W and file register F. Again based on D value. After logical ORing, the result either it will be stored in a working register W or file register F based on D. If D is equal to 0, after logical ORing, the result is stored in working register W, otherwise it can be stored in file register F itself. And next one is move F, D. That means move F. That means move the content of file register. Move the content of file register either to working register W or file register itself. That is, it depends on bit D. Move the content of file register F either to working register W or it is to file register. That is, a purely depends on D itself. So that's it. Next, move WF space F. That means move the content of working register W to the file register F itself. And next one is no, means no operation. Next, RLF F, D. That means rotate left the content of file register F through carry. I repeat, RLF means rotate left through carry the content of file register F. After that rotation operation, the result is stored in that file register itself or it can be stored in a working register. Again, that is depends on D itself. Opposite to this one is RRF. That means rotate right through carry the content of file register. Again, based on D value, the result is either stored in a file register F or it can be stored in working register W. Next one is SUBWF sub WF F, D. That means subtract working register W from file register F. Subtract working register W content from file register F content. After that subtraction, whatever the result we was getting at the output, that can be stored either in working register W or it can be stored in file register F. That is again purely depends on bit D. If D is equal to 0, the result is goes to working register W, or D equal to 1, the result is goes to file register F itself. Next, swap F, D. That means exchanging of nibbles of file register F itself. That means upper nibble is moved to lower nibble and lower nibble is moved to upper nibble of selected file register. After swapping, The result is again stored in a file register F itself, or it can be stored in working register W. That was it depends on again bit D. And next one is XOR WF F comma D. XOR means exclusive OR between the content of working register W and file register F. Again based on D value, the result can be stored in working register W or it can be stored in file register F itself. All these comes under byte-oriented instructions. And coming to the next one, bit-oriented instruction, just I have only 4. In that first one is BCF means a bit clear. Bit clear of a selected file register F. See here friends, an example is BCF F comma B. For better understanding, I can write like this: BCF status comma 3. So here in place of F we have a status register. In place of B I have a value is 3. That means by using this instruction I am going to clear bit 3 of status register. The meaning of this one is clearing of bit 3 in status register. So I am not touch the rest of the bits what I have in a status register. I just go and modify only bit 3 of a status register. That means bit 3 was clear. That means bit 3 is loaded with 0. That's the meaning of this. Opposite to this one is the next. BSF means a bit set. Bit set of file register F. So instead of this, if I write an instruction is BSF space status comma 4. That means I am going to set bit 4 of a status register. So that is the meaning of this. And next one is BTF SC space F comma B means a bit test of F. Bit test of F. Skip if it is clear. Alright, example of this. This is a program friends. So somewhere else here I have an instruction BTF SC space status comma 2. My instruction is like this: BTF SC space status comma 2. Straight away I can go and check second bit of status register. I can go and check the status of second bit of status register. If it is a clear, I skip this instruction. Otherwise, I continue the execution of this. That's the meaning of that. Opposite to that, next one is the BDFSS space F comma B. So again, if I write it is a BDFSS status comma 2. That means I straight away go and verify second bit of a status register. If it is a set, I skip this instruction. If it is not set, I will not execute that instruction. That's the meaning of that. So these are my bit-oriented instructions. Coming to the last, that is constant or literal and control instructions. So see here friends, add LW space K. That means here L represents a literal. So add a constant or literal to working register W. After completion of addition, the result again stored in W itself. W is nothing but working register. So in this case, I need not write a D because I can't send my result into some immediate data. So that's why I always send my result to working register W. So that in the instruction itself, I never write D. And next, AND LW space K. That means AND logical between working register W and specified literal or a constant. After logical AND, the result goes to W itself. In these cases, no doubt, these values are 8-bit. So here and here, it is an 8-bit. And next one is call K. So this is an instruction is used to call a subprogram. By execution of this instruction, we shift our execution to subprogram from main program. So here, this K value is 11-bit address. K value is 11-bit address. So as usually, what we know about the call instruction, either in 8086 or 8051, the same thing here also we are following. But here important thing is always the call instruction is used to call a subprogram into main program. In that case, always our operand is a 11-bit constant or 11-bit literal or 11-bit immediate value. That's it. Next is CLR-WDT means a clear watchdog timer WDT. By execution of this, watchdog timer is loaded with the 00H. And next go to K. So go to is simply unconditional jump instruction. Go to is simply unconditional jump instruction. Go to K, jump to K. So here also this K is a 11-bit address. And next IORLW space K means inclusive OR between a literal or a constant 8-bit and working register W. After completion of that inclusive OR, that means logical OR, the result is goes to working register W itself. And next one is move LW comma K. That means move the constant or literal value into working register W. And next one is RET FIE means return from interrupt service routine. RET for return, FIE means return from interrupt service routine. So that is RET LW comma K. That means return with literal K. So that means you return to the main program. In the process, whatever the constant value we write in the instruction, that was copied to working register W. In previous case, just you are written from subprogram. Now if you want to return to the subprogram or you written from it, we do one more thing, that is whatever the constant value we written in the instruction, that was copied to working register W. Here also this K value is again 8. And next one is this is the last part, return. That means return from subprogram. In our 8086 we are using simply RET, or in different controllers also we are using RET instructions. So, but here we are using instruction is straight away return itself. Return is used to return from subprogram. Next one is a sleep. This is the instruction to send our controller into a sleep mode, which is a power saving mode. So here that what I write in here is go into standby mode. That means a sleep mode. So which is one of power saving mode of our PIC controller. Next is sub LW comma K. That means subtract working register W content from a literal or a constant. After completion of subtraction, again the result is goes to working register W. And coming to the last, XOR LW space K. That means do logical exclusive OR between working register W and a constant K. After completion of a exclusive operation between these two inputs, the result is stored in working register. In these two cases, here the K is a 8-bit immediate value, and here also K is 8-bit immediate value. So I hope you understand. These are the instructions which are present in the instruction set of PIC controller. So thank you very much for patient listening.